Welcome, guys, to lesson in Laplace transform. So, fair warning, I am not a mathematician, so this will be strictly relevant to chemical engineering and how Laplace transform is used in chemical engineering studies. So, to begin with, we will introduce what Laplace transform is, talk a bit about the definition, then we will do some examples, and that will be all for this video. So, what is Laplace transform? Laplace transform is a mathematical technique that converts functions from the time domain into the frequency domain, simplifying the analysis of systems and differential equations. Our main aim, so the main aim of Laplace transform is to simplify differential equations, which are very important to chemical engineering, mass balance and energy balance. The Laplace transform is an integral transform. From here you can understand that a integration will be involved that takes a function ft in time domain defined for t greater than equals to 0. This is intuitive because we cannot go to negative time. We can go theoretically, but that is of no use in practical sense, and transforms it into a function fs in the frequency domain. The mathematical relationship is given by f of s is, which is Laplace transform of ft, is equals to integration over 0 to infinity ft into e to the power minus st dt. This formula we use to transform a function from t domain to a function in the s domain. Of course, the integral should exist, otherwise there will be a no Laplace transform for the said function. So here t is the time variable with units of time, s is the frequency with units of time inverse, thus s into t, which is at the power of which resides at the power of e to e, is a unitless quantity. So let us see how Laplace transform can be used to transfer a function from t domain to the s domain or the frequency domain. We begin with a very simple function where ft equals to 1, a constant. Now we proceed to write the structure or the formula of the Laplace transform. F of s is equals to L of ft is equals to 0 to infinity ft e to the power minus st dt. Now what we will do, we will put the value of ft here. So f of s becomes integration over 0 to infinity 1 into e to the power minus st dt, which is nothing but integration over 0 to infinity e to the power minus st dt. Moving forward, if we integrate it, we will get minus 1 by s e to the power minus st, the lower limit being 0 and the upper limit being infinity. Now putting the upper limit and lower limit, we have minus 1 by s into e to the power minus infinity minus e to the power 0. The first term tends to 0 and the second term is 1. So we have minus 1 by s into minus 1, and thus f of s is equals to 1 by s. So from it is very clear to you that ft is not equals to fs. ft is equals to 1 corresponds to fs is equals to 1 by s. Just like, say, we have a captain of our cricket team is Shreyas Iyer, and if the captain of our football team was Sunil Chhetri, they both are captains, but they are not the same people. Laplace transform does what? It takes a t independent variable function to a s independent variable function, and they correspond to each other. They are related to each other, but they are not identical. So that you should keep in mind. Moving forward, let us do another example. Here we are again taking a simple function ft is equals to t, a linear function. Now if we put the structure of the Laplace transform in place, we have fs is equals to L of ft is equals to 0 to infinity ft e to the power minus st dt. Moving forward, we have f of s is equals to 0 to infinity, putting the value of ft is t into e to the power minus st dt. Now we have two variables t and e to the power minus st inside the integral. So we have to proceed using integration by parts method. Here we are taking t as the first function and e to the power minus st as the second function. Now the integration can be done as f of s, first function unchanged, that is t, then integration over 0 to infinity of the second function, which is e to the power minus st dt, then minus integration of derivation of the function, which is ddt of t, and integration of the second function, which is 0 to infinity e to the power minus st dt. Moving forward, we have evaluated the first integral, which is minus t by s e to the power minus st 0 to infinity, and for now we are keeping the second integral as it is, which is 0 to infinity ddt of t 0 to infinity integration of over 0 to infinity e to the power minus st dt. The first term on the left hand side contains a linear term which goes to infinity at the upper limit, while the other exponential term goes to 0. Now we have a conflict. We have a product of t into e to the power minus st. T is going to infinity, but e to the power minus st is going to 0, and we have a impasse where in a product a function is going to infinity, another is going to 0, and 0 by infinity is undefined. But we have to think in terms of graphical method, that when we plot a linear function with a graphical exponential function, the exponential function will rise up or fall very fast compared to the linear function. Thus the exponential function will dominate. Here the exponential function is going to 0, thus the whole product will go to 0. Hence we can write f of s is equals to 0 minus 0, the upper limit is 0 and the lower limit is obviously 0, plus 1 by s 0 to infinity 1 into e to the power minus st dt. Again integrating, we have f of s is equals to minus 1 by square e to the power minus st 0 to infinity. Putting the limits, we have minus 1 by s square e to the power minus infinity minus e to the power 0, which is f of s is equals to minus 1 by square 0 minus 1, which is f of s is equal to 1 by s square. So the Laplace transform of t is 1 by s square. So in this video what we have done, we have discussed the definition of Laplace transform in brief. We have done some examples with very basic functions, both of them being linear. In the next video we will try to cover nonlinear and hopefully some trigonometric function, which will be up very soon. See you all then. Thank you for watching.